My name is Carlos. Thank you so much for having me. And today I have the pleasure of talking about tools for the analysis of RNA 3D and 2.5D structures. So we all know that there's a very strong relationship between nucleotide sequence of an RNA and the 3D structure that it's going to adopt. Obviously, um, getting information about the 3D structure is very important for understanding its function, especially when it comes to non-coding RNA. If we were to look at a 3D structure and see how it's composed, we notice that it's formed by events called base pairings, which are hydrogen bonds forming between pairs of nucleotides. So we just chopped up the 3D structure and put in some base pairs here, where the hydrogen bond is shown in yellow. Very interestingly, Leontis and Westhoff found that by looking at many 3D structures, you could note some regularities in how these bonds are formed. And they came up with a nomenclature that would help us categorize the different ways that two base pairs can interact. And this is called the Leontis-Westhoff notation, where each residue is modeled as a triangle, where each edge is given an arbitrary category. And by noting where the hydrogen bond forms, respective to these triangles, we can come up with an alphabet of base pairing interactions. Most computational methods and experimental methods try to understand how what we call canonical base pair. So this specific type of orientation is called the canonical Watson-Crick base pair. But it turns out that many other base pairs are possible, and they're often very important in understanding 3D structure. So these are the ones we call non-canonical, anything that's not Watson-Crick. So obviously, many of you know that understanding the interactions that form a 3D structure is a key challenge in the field. It started by trying to predict the 2D structure, what we call the set of canonical base pairs. So this is an example of a 2D structure. So given a sequence, we have many notable tools that can do this quite efficiently. But the story doesn't stop there, because if we were to take the first structure that I showed in 3D and plot all the different interactions that are formed, all the different base pairings, we see that it's not the complete story. So another challenge comes up, and that's what we're calling predicting the 2.5D structure. So the enhanced or augmented set of base pairs that we don't get if we just look at 2D structure. And there are notable tools in this area as well. And a big challenge here is that we don't really have very good energy estimates for these types of interactions, the non-canonicals. So a lot of the methods really depend on more data-driven or statistical approaches. And going all the way to 3D, there's also been a lot of focus. So and the main sort of hub for that is the RNA Puzzles hub. So it's a CASP-like evaluation for 3D structure prediction, where when an RNA is experimentally solved through crystallography or NMR, the structure is withheld for some time and the sequence is published, and anyone who's interested in participating in the challenge would come up with a computational prediction of what that sequence is going to fold into in 3D. And this is submitted, and then the true 3D structure is published, and obviously a ranking of tools is performed. And there are many notable tools in this regard. What's nice is that the RNA Puzzles challenge also comes with some toolkits that are that you can use to evaluate in many different ways 3D structure predictions, and many challenges are released regularly. So if you're interested in participating, I encourage you to go to rnapuzzles.org or RNA Puzzles Toolkit to learn more about this. And I'm going to talk a little bit more about some connections between this and other types of structural challenges. And the last one I wanted to mention is that, well, we also want to understand how RNA structures interact with other types of structures. So in this case, small molecule, but it could be proteins, ions, and many even other RNA. So this is kind of like the next level of structure prediction. And we see, interestingly, that the non-canonicals, at least in this binding site, but also it's been shown more generically, are enriched in interaction hubs. So understanding RNA at the complete set, not just the secondary structure, is very important. And again, there are tools that are working toward this, and this is sort of like a newer challenge. The main thing I want to present here is RNA glib and how we want to connect it to the RNA Puzzle challenge. So RNA glib is a Python toolkit that helps people work with RNA 2.5D graphs. We find that this is understudied, but actually has a lot of potential, because you get the convenience of the discrete representation of RNA that the 2D level represents. So understanding RNA as a set of base pairs, which is a really strong prior. And it also has richer structural information that you would typically find when working at the 3D level. So RNA glib is still a work in progress, but we have already developed quite a few features. So it's going to be very easy to install. It's going to have a connection to an up-to-date repository of annotated RNA structures at the 2.5D level, as well as any kind of function that we can attach to these structures and substructures. And it's going to also interact very nicely with PyTorch, so that anybody working on predictive models and graph convolutional networks can connect this data to any kind of model they develop. We're also providing some implementations for unsupervised learning. So these are functionalities which help you compare RNA 2.5D substructures. We have fast visualization and a set of baseline models and benchmarks to help the community have a standardized goal. So at the core, we have a set of 2.5D graphs that we build from a public tool called X3DNA DSSR, and which we update and host regularly at our servers. And the package is going to automatically connect to these and download the data for you. So you can just import the data loading module, create a data set. So the standard one is the graph data set, which contains a non-redundant set of RNA 2.5D structures and a lot of associated information. So you can look at, for example, the node features that we've encoded here. There are many. Some of them include, for example, whether a nucleotide is binding a protein, whether which type of secondary structure it's nested in, if it's chemically modified, and so on. So this data set contains 814 graphs because it's a non-redundant set. And we've done some filters for removing very small graphs and graphs that are, just dangles. So we've done some cleaning and curating. And the nice thing is that this dataset object, you can work on it on its own to do analysis, or you can pass it to a PyTorch data loader if you wanted to train a machine learning model, for example. So I'm going to show some basic ML setups for that. So once you've built your data set, you can pass that to our supervised loader object, which is going to be able to digest that data set and pass it to any machine learning model you want. If you wanted to focus on specific prediction targets, so if you wanted to build a model that predicts whether a substructure binds to protein, you simply select that attribute. And if you want your model to use specific features of the graph, you can say, all right, I want my model to pay attention to, as input, what nucleotide I'm in, but you can also use other features. So we're going to have as input nucleotide features and as output whether or not we're in a binding site. If we don't have enough data, or if we wanted to simply train a model without a supervised target, we've implemented some supervised learning functions that are published here, which basically iterate over the data set in pairs of nodes and compute similarities. Using those similarities, we actually output a model that embeds RNA 2.5D substructures, so kind of in a similar manner to Word to Vec or even protein to Vec. And we've also implemented some common architectures, specifically graph convolution networks, since we're working with graph data. So you can build classifier models and embedder models. So embedder models simply take a graph and output vector embeddings. Classifier models take those vector embeddings and output a prediction decision. So we can connect those two. We keep them separate because we want to be able to train them separately. So the training is also very simple. You just import PyTorch and you create your optimizer. Now that you've built your model object, you can pass it to this training function. You pass your optimizer and your loader, and you're good to train. If you wanted to take advantage of unlabeled data in an unsupervised manner, which has been shown to be very, very effective, you can simply apply this line of code before using the supervised training to train your embedding model on some sort of node similarity function. So it's going to try to produce similar embeddings or vector representations for nodes that have similar structures. And once it does this, you're very likely to do a better job on the supervised task. And something we're very excited about is that we want to be able to connect this to structure prediction. So if we think of our input as a graph, which is just a line, we can basically a sequence is just a linear graph. We can come up with a task of predicting which of those nucleotides form base pairs. In the graph machine learning world, this is called link prediction. So we've built data loaders that help you load these graphs in a link prediction setting, as well as some basic link prediction models. And we can take the 3D structure or the full 2.5D structure and see how well we're able to reconstruct the full 2.5D by looking at which pairs of nodes we got right and which ones we didn't. Finally, we have some simple visualization tools that let you take your data set, select a graph, and basically draw it using NetworkX API. So obviously it's very rudimentary, but at least it helps you get a quick view of what's going on in terms of the full canonical and non-canonical interaction set. We're building some basic benchmarks, some basic benchmark tasks. So, you know, the community can decide to take on this challenge of predicting whether RNA binds with small molecules, whether they bind with ions, using these 2.5D graphs as input. Okay, so if this is interesting to you, then and you'd like to try it out, just send me an email and we can give you access. We haven't published the tool yet, but we're happy to have more collaborators and more feedback. We're still working on more features, so further integration with RNA puzzles, benchmarks for base pair prediction task, and some more sampling functionality, as well as it's going to be public on PyPy, and we're going to improve our visualization. So with that, I'd like to thank my collaborators and funding sources, and thank you again for attending.